takes a minute or two. Perfect. All right, so we are recording. So thank you again to those of you who are able to attend virtual lab notes today. We're very excited to have Dr. Bing Zhang from the Department of Physics and Astronomy in the College of Sciences as our presenting speaker. My name is Corey Nelson. I'm the Director of Development in the College of Sciences, and I work on our community outreach and engagement within the college. And I work obviously at UNLV as well. So just a few reminders before we get started. Make sure throughout the presentation that you keep your microphone muted and your camera off. The buttons at the bottom, the microphone and the camera, should both be in red. Use the chat function at any time if you have any questions throughout the presentation. We've reserved the last 10 to 15 minutes or so, depending on the length of the presentation, for a question and answer session. So we will get to those questions throughout. If during the presentation you have any technical issues, you can always check out the support link at support.google.com/meet, and you should be able to find answers to any questions there. You can also send me a little chat and I'll see if I can help at all. Again, we are recording this presentation, so if you've just joined, just please note that we are recording and that it will be available on the College of Sciences YouTube page after the presentation, about a week after the presentation, and also on the College of Sciences website. So for those of you who haven't joined us before, as you may know, we do these monthly, and please join us for next month's topic. We'll be getting dirty using wastewater to understand the spread of human disease. And our speaker will be Dr. Edwin Oh, who is an associate professor of neurogenetics and in the Precision Medicine Lab in the UNLV School of Medicine. And he is also a faculty member with the Nevada Institute of Personalized Medicine, which is part of the College of Sciences. So mark your calendars for that on April 28th. But in the meantime, I wanted to introduce our current speaker to everybody, Dr. Bing Zhang. And I'm going to give a short bio with Dr. Zhang. So Dr. Bing Zhang received his PhD degree in astrophysics in 1997 from Peking University, China. After taking postdoc positions at NASA Goddard Space Flight Center from 1998 to 2000, and the Pennsylvania State University from 2000 to 2004, he joined UNLV in 2004 as an assistant professor. He was granted tenure in 2008 and promoted to full professor in 2010. Dr. Zhang's research covers a wide range of topics in high-energy astrophysics. Besides fast radio bursts, his recent research interests also include gamma-ray bursts and electromagnetic counterparts of gravitational waves. He has published more than 450 papers in refereed journals and is the author of the Cambridge University Press book, The Physics of Gamma-Ray Bursts. He is one of the most cited scientists in his discipline with more than 28,000 citations and an H-index of 87. He is an elected fellow of the American Physical Society and a UNLV Distinguished Professor. And also proud to say he's the Associate Dean for Research in the College of Sciences at UNLV, and we love working with Dr. Zhang. He's a great asset to us and one of the most published professors that we have at UNLV. So I'm very excited to welcome Dr. Bing Zhang.
Okay, thanks, Corey, for the introduction. Let me try to share the screen. You can see my slides now?
Yep, we can see them.
Okay, let me do the full screen. All right, thanks everyone for joining this talk. I'm going to talk with you about fast radio bursts. The title is A Mystery Being Solved. Astronomers like mysteries, so from the dawn of the humankind, our ancestors look at the sky and try to understand how celestial bodies move and why. And in contemporary astrophysics, we have a lot of mysteries. In cosmology, we have big picture like dark matter, dark energy. In exoplanet science, we have a lot of new discoveries, a lot of mysteries. And this slide, can you guys see the arrow pointing?
Yeah, we can see that.
Okay, good. So in this slide, I'm just sharing some of the mysteries in the discipline I'm working at the high energy astrophysics. So we know that there are a lot of exciting stuff. For example, neutron stars spinning, those are the pulsars. We have black holes in the stellar scale accreting X-rays. We have huge black holes in the galactic center making active galactic nuclei, AGNs. We have collisions, we have explosions of stars making supernovae. We have collisions of stars, two neutron stars or neutron star black holes. Those make gravitational waves. And a very interesting, exciting aspect of this field is that a lot of transients. So our universe looks like it's in a steady state, but you really look at in detail, there's a lot of transients, which means that a lot of objects are varying in brightness within a variety of time scales from milliseconds all the way to months and years. So for most of mysteries, after this many years of discovery and studies, we actually at least know what is going on. For example, for actually binaries, actually sources, we know there is a black hole there accreting from a companion star. For so-called AGNs, we know there's a black hole sitting right in the center of the galaxy. However, this topic I'm going to talk about today, the so-called fast radio bursts, are something we essentially know nothing. So that's why it is called a mystery. And it is most exciting to astronomers because we have a lot of chance to really figure out what is going on. And solving mysteries, we need telescopes and minds. So basically observers and theorists. So here's Galileo, who invented the first telescope, and here's Einstein, who is brightest mind in human history. We need to combine these two approaches and look at this is the entire electromagnetic wavelength, and we have different types of telescopes covering different energy bands from radio to infrared optical and X-ray and gamma rays. And to solving the mysteries, I usually think that because myself is a theorist, so my job is quite similar to a job of a detective. So what this guy is doing is just based on whatever fingerprints, footprints he collected, and sometimes there is a smoking gun, and eventually he can figure out what is the crime scene. So we theorists are trying to do the same thing. We are using logic, we are using physics, and we ask observers to provide the data. Okay, fast radio bursts. So this is the one slide introduction. This plot is the famous first FRB. Back then it is called the Lorimer burst. It was discovered by my friend in University of West Virginia, Duncan Lorimer, and colleagues. They used archival data from the Parkes telescope in Australia, 64 meter telescope, and they found that there was a radio pulse, very short, so typically the duration is milliseconds, and highly dispersed. So we know radio waves propagating in the universe, they do not travel with the speed of light because the universe is filled with plasma, and the higher frequency waves will arrive later than the lower frequency waves. And this delay, this is called a dispersion, and amount of delay tells you how much electrons are along the line of sight. So at least some sources repeat. So this very first one, just one-off event, but there are other FRBs they repeat. I'll get back to that. And most of the FRBs are from cosmological distances. I'll explain that. And they are the brightest radio bursts in the universe. And they have very high rate, how high it is? If we have a all-sky radio telescope array, so which means that if we have a lot of telescopes pointing towards the 4 pi degree of the entire sky all the time. So every day we at least will discover several thousands and probably more than 10,000. So it depends on the sensitivity of the telescopes. However, the truly detected ones are much smaller because radio telescopes can only stare at a small patch, small region in the sky. So the physical origin is unknown, so I'll guide you through this entire history, well, very short history of this field, people trying to answer several questions. Okay, here I want to show you a movie. Actually, instead of showing it, well, it's rather listening to FRBs, because FRBs, it is radiated in a gigahertz band. Typically, that's the radio, the band for radio telescopes. But we can scale down to the frequency range which our ear can hear. Unfortunately, this software does not allow me to do this. Actually, Corey has kindly agreed to show that for me. So, Corey, can you take over?
Yeah, I'm going to switch my microphone off and I'll present it. So give me just 1 second.
Yeah. It does not work. I cannot hear it. Can others hear it? Okay, thanks, Corey. So what you heard is so most of the sound you heard is noise, but you can hear the very brief chirp signal. So that is the FRB. You go back to the presentation mode. Okay, so you can have a general impression how short those FRBs are. Oops, let's move on. So because we are solving mysteries, we are trying to address several questions, 4 of them altogether. The very first one is, are they astrophysical? Because in astrophysics, there are several occasions you discover something and it turns out that they're not real. And for FRBs, it took a while. The main reason was that this was the FRB. This was the very first burst called the Lorimer burst. And later, the same telescope, this is the Parkes 64-meter telescope in Australia, they discovered something else. You can see they look very like FRBs, and they also are highly dispersed. However, they were detected by many beams. There are 13 beams in this telescope. So usually FRB, because they are far away, you can only detect it from 1 beam. But these guys, which are called peritons, Somehow they got this name, which means that mythological, that they're not real. So sometimes these peritons could be detected in all 13 beams. So they already knew that these could not be real. So these must be terrestrial or artificial. And the question is, if these guys are artificial, and how about these guys? So this was an example of a periton. So you can see these all 13 beams. They all detected this little pulse, and they are all highly dispersed. And it took a long time, actually, from 2007. This paper was actually finally published in 2015. What they did was trying to, first they wanted to see what is going on, and they plotted all kinds of comparison plots. This is one of them. So you can see this is the time when those bursts were detected, and this is the number. And they grouped the two types. One type is these peritons detected in multiple beams. It turns out they all mostly occur around the noon time. This is the local noon time in Parkes Observatory. The so-called FRBs, the other guys, on the other hand, they are evenly spread out in all the other hours. So they did a lot of experiments. They finally found out that the origin of peritons is actually the microwave ovens. Some of the astronomers, some of the local guys, they heated their food, but maybe in a hurry or something, they're impatient before the heating is over. If somebody open the microwave oven door, and a signal is sent out to the telescope, and these are the peritons. And they actually did the experiment and show that those indeed produce peritons. But we still don't understand why microwave ovens can produce peritons. But this plot actually solved the problem. So instead of saying that they're artificial, we can say that they are actually astrophysical. We do have those intrinsic FRBs, which are very different from these guys. The second question astronomers want to answer is, are there multiple types? As I just said from the very beginning, the Lorimer burst was a one-off burst. Actually, they followed up for 90 hours later in the same direction, and they never found anything from that direction. On the other hand, some other FRBs, this is the famous Arecibo FRV, FRB 121102. So this one was observed by the 305-meter Arecibo telescope, which is more sensitive. And it turns out that during that observation, there were 11 events happened within several days. So this suggests that at least some FRB sources repeat. Then the question is, are there two types? So people tried to look for the differences, and this was a very nice paper by the Zhang. Zhang is a Canadian telescope array, detect a lot of FRBs. And their collaboration showed the distribution of the width, which is the duration of these bursts. And they found that these one-off ones are relatively short. And for repeating ones, they are relatively longer. So repeating bursts are wider. However, some repeating bursts are very narrow. So then the question is, if one source does not repeat, for example, this one does not repeat, can we ever say that it will never repeat? So this is the main problem, because if you don't see it, it may repeat tomorrow. So there are two groups of astronomers. One group believe that every FRB is repeating. The other group is thinking, oh, maybe there are two different categories. So this is still an ongoing question, mystery. A lot of more work needs to be done. And very interestingly, some of the repeating sources, this is one of them. I didn't write down the name. It's a telephone number, so you don't need to remember it. This one had a period, so it's called periodic FRBs. If you look at the observation time and the detection time, and this is for the chime again. So they found that the bursts were detected within these windows of a 16-day period duty cycle, and within 16 days, there's a 5-day active window. And most of the sources bursts were detected inside that window. And this is the confirmation with other telescopes, and we can find that they're all falling into the window. Some of them are slightly off outside, but the majority of them are inside this 5-day window. Then there are a lot of discussions among theorists what is going on, and there are two major scenarios. One is that the FRB source might be in a binary system, and this 16-day period is due to the binary orbital motion. And another possibility is that the FRB source might be a magnetar. The magnetar is precessing. So the emission beam is doing this 16-day precession. So we still don't know what is going on. Okay, the third question is, where are they? So this is a major question for all the sources. So this plot shows our cosmic address, the Earth. So we are in the vast universe, and there are so many these filament structures, and one of them is called our local supercluster. There are millions of those clusters, and within this cluster, there's, look at here, there is a local group of galaxies, and we turn out to be within this local group. There are maybe 50 to 100 galaxies, and there are two big ones. Ours is the second largest one, so this is the Milky Way, and it turns out the sun is far away from the center of the Milky Way, and we've got 8 planets, and our Earth is the third one. So everybody knows this. However, for FRBs, the natural question comes, because for radio telescopes, usually the resolution, angular resolution is very poor. So you cannot really pin down where it comes from. We can just guess. So 5 possibilities. One is terrestrial, it just comes from the Earth. The second is from the solar system, from the Milky Way, from extragalactic, but not too far away, like our local group. And finally, it is cosmological, means it is everywhere in the universe. So this was the question raised, and actually there are models for all 5 possibilities. Okay, and where are they? There's actually a very interesting hint from the dispersion measure. Sorry that I have to show some formula on this page, but they're straightforward. So dispersion measure is the amount of delay between the high frequency and the low frequency waves. And this amount of delay is defined by something called DEM, which is dispersion measure. So you can, given the 2 frequencies, there's a constant file, 4.15 milliseconds, and amount of DEM will tell you how much delay it is, say, between these 2 frequencies. And we know that dispersion is caused by the cold electrons in the universe. So basically, this DEM is the integration of free electron number density along the path. So basically, this is the column density of electrons along the line of sight. So this tells us how many electrons are out there. So this DEM, usually we can break down in several different terms. We have our own Milky Way electrons, and that amount of DEM is typically small. So, so this is the galactic pulsar DEM, the blue dots. Near the galactic plane, of course, it is larger because we are in the plane. But at higher galactic latitudes, they are pretty low. This DEM value is several tenths. However, FRBs are detected at higher galactic latitudes, and their DMs are several hundreds to thousands. So it means that our galactic electrons are not enough to cause this dispersion. We need something else, and we can include the halo from the Milky Way. We can include the host galaxy from those sources, but that's still not enough. We still need a large portion of electrons coming from the intergalactic medium, which means all the electrons in the universe. And one can really calculate this. I will skip the details, but this is the scaling law. So roughly speaking, dm/IgM is proportional to redshift. What is redshift? Redshift tells us how far away a source is. At redshift 1, basically the light travel time is 7.8 billion years. So say z equals 1 is already at very large distance in the universe. And you can see for z equals 1, dm/IgM should be 855. So observationally, we can see that these guys are several hundreds and sometimes 1,000. So basically, redshift, it could be from 0.5 all the way to 2 or 3. So this means that at least from dm, we can already guess the FRBs should be extragalactic and probably and very likely cosmological. The firm confirmation actually came from the localizations. As I just said, in the radio band, the angular resolution is very bad, simply because the angle we can differentiate is scales as the lambda wavelengths divided by the aperture of the telescopes. Even though the radio telescopes are typically larger than optical telescopes, the lambda, the wavelengths of radio wave is much longer than the optical wavelengths. So typically the radio band has a poor resolution. Unless you can do VL, a very large array, VLBI, very large long baseline interferometry. The bottom line is, instead of using one telescope, you use many telescopes. This is the VLA in New Mexico. You can place a telescope here and another telescope, say, 1,000 miles away, and use them to observe the same source simultaneously. That way, you effectively increased the aperture of the telescope, and then you can narrow in to have a very good resolution. So this happened to the first repeater, because after detecting 11 bursts, people know that that one will repeat again. So they used many telescopes to stare at the same location, just wait until the next event happened. And finally, it happened. This is the region, the very small error box of the radio band. And it turns out that there is a galaxy there. And one can measure the redshift of that galaxy is turned out to be 0.19, 0.2. So this is indeed cosmological. And after that, this ASCAP team from Australia, they're using several telescopes with a very large separation. So they, because it's the same team, they basically observe any region in the sky simultaneously, always stare at the same sky region simultaneously. When an FRB happens, all the telescope will detect them, and in the meantime, the FRB will be localized. And these are the localization error box, and they're all associated with a galaxy. Sometimes it's a star-forming galaxy, sometimes it's a spiral galaxy, so all kinds of different galaxies. And their redshifts are as we expected. So this is the redshift, measure the redshift. This is the DM, dispersion measure. Indeed, the data is consistent with this theory. So there's a linear law there, even though there's a scatter. So this observation actually finally confirmed the cosmological origin of FRBs. So back to this plot, where are they? We now know that they are from extragalactic and cosmological distances. That does not mean that we do not have FRBs in our galaxy. It's just a matter of the majority of them, what we see, are from the cosmological distances. Actually, in the following, I'm going to tell you that there was one FRB detected from our own galaxy. That was the major breakthrough last year. Okay, the fourth question is what make them. This problem is even more difficult to address simply because you have very limited information, and this is a detective's job and trying to figure out what is going on, and different authors, different theorists have their different favorite models. So this is the incomplete list of the models, including repeating sources, catastrophic sources. I will not read off these, but you can see flaring stars from some magnetars, from some cosmic combs, from some pulsar magnetosphere and neutron star asteroid collisions. Catastrophic ones, the collapse of neutron star to a black hole, some mergers, neutron star mergers, black hole, neutron star mergers, a lot of possibilities. And of course, aliens. There are papers talking about aliens, but this one is ruled out essentially. But I'll get back to aliens by the end of the talk. And there is actually a website. So this is the wiki site for FRB theories. Somebody collected all these models there and their pros and cons and those kind of things. Yeah, just for fun, I think. Right now, there are more than 50 models. For a while, from the early stage of this field, the number of models are more than the number of birds. We only had like 10 birds, and there were already 30 models back then. But of course, we have a lot more birds now. This is no longer the case. But the second one is even more interesting. Number of models more than the number of theorists. This is saying that, yeah, so the same theorists can probably propose multiple theories. So look at me, so 1, 2, and 3. I got 3 of them. So these models are very different have very different ideas. But the common feature, unfortunately, is that the majority of these models will be wrong. So they're not the correct interpretation of FRBs, simply because nature cannot make FRBs using 50 different methods. Of course, eventually, some will survive. So I could imagine at least 1, probably 2 or 3 models will, even 5, optimistically, but not 50. Okay, so this table is from my recent review. So it compares the 2 fields, the gamma ray burst field and the FRB field. So these 4 questions, they went through essentially the same path, and it took several years to address each of them, but FRB field actually speeded up a lot. So you can see for RA astrophysical, for GRBs, it took 5 years, and for FRB also took 5 to 8 years. The multiple types, it took a while. So this is already almost 20 years, but the FRB field is faster, so this is 10 years. And where are they? It took 20 years to, well, if we start from the discovery, so it takes 30 years to find the location of long GRBs and another 15 years to find out the location of short GRBs. FRBs, they did very quickly. Once the repeater was found, 1 year later, they were localized. And now we also found some galactic FRB. However, the last question, what make them? For GRBs also took 50 years to finally figure out the short GRBs are from neutron star mergers. And for FRBs, I was very pessimistic simply because FRBs are fainter in terms of energy, it's much less than GRBs. And they don't have a smoking gun, say, counterpart. For long GRBs, they are associated with supernovae, and short GRBs, they are associated with neutron star gravitational waves. Once you detect those, then you nail down the origin. And for FRBs, they're at cosmological distances, and they are very faint, and there's nothing else you can detect other than radio waves. So initially I said, they probably take decades to figure it out. But again, surprises happened. So only after 3 years they were localized. This was last year. One galactic FRB was detected. And because it is galactic, we know where it is. And it turned out that that FRB was associated with a magnetar. So we at least know that magnetars can make FRBs. Whether other things can make FRB, we don't know, but at least we found one source. So what is a magnetar? Magnetar is a neutron star with the surface magnetic field of 10 to the 15 Gauss. 15 Gauss is the highest magnetic field strength in the universe. So our sun is 1,000, our Earth is of the order unity, and for normal neutron stars it's 10 to the 12th, but 10 to the 15th is very, very high. And these guys, so they're born in supernova explosions probably. So massive stars, but not very, very massive. Very, very massive ones will make black holes right away. But massive stars, but not too massive, will make neutron stars. And neutron stars, they will show up as pulsars mostly. But a fraction of those neutron stars, maybe 20% of them, will produce much heavier, much stronger B fields. So those are the magnetars. And magnetars have been the main suspects for FRBs. So out of those 50 models, actually the magnetar model has been one of the top choices, simply because magnetars, they are powered by magnetic fields, and they do emit bursts, but they emit the hard X-ray and soft gamma ray bursts, not radio bursts in the past. And some of those bursts, so this is one of them. This is a giant flare. This one has a very short, hard spike, and the duration is milliseconds. This is in gamma ray, soft gamma ray band. So we knew this before, and very naturally, many people will think that, okay, because this one is a brief gamma ray burst, there might be a very short radio burst associated with this. So that was why this model was quite popular. However, there was a major drawback of this model, because this exactly same event was observed by a radio telescope. If there is a bright radio source, radio burst occur, it should come at this time. It depends on the dispersion measure, but nothing was found. Nothing was found. So that was why, even though the magnetar model is quite attractive, this non-detection makes people think, oh no, probably it is something else, not the magnetars. And then there comes to this April 28th event. So this is the galactic magnetar, SGR, this telephone number. And so during April last year, a lot of telescopes from, say, Swift, Fermi, InSight, this is the Chinese hard X-ray telescope. This is the NASA's hard gamma ray. This is NASA's GRB detector. And ground-based, we have STARE-2 from Caltech, CHIME from Australia, and FAST from China. So there are a lot of other observations too. So I will describe how these telescopes contribute to this major discovery. Swift first found that this guy started to become active, which means it started to release a lot of gamma ray bursts. So I collaborated with my international colleagues, most from China, but also people from US and Spain and New Zealand. So we actually organized such kind of observational campaign. So we not only use the radio telescope, we use this 500-meter, this largest aperture radio telescope to observe it. We also use the optical, we use X-ray, of course, we all use the gamma ray. Fermi data is public, so we can process those. Because we knew that it started to become very active. So back then, my goal is, okay, let's just bet, because we don't know when it will make a burst. So let's just bet and just try to observe that source. Maybe during one of the windows, some gamma ray burst will happen. If that gamma ray burst happens, then we can immediately say whether or not there is a radio burst associated with it. So these are the 4 sessions we observed. The earliest one is actually from April 16th, and we did it again on the 26th, and we did it again on 28th. Actually, after we finished, at this time, that FRB happened. So yeah, there were many gamma ray bursts, but most of them, they don't have fast radio bursts. Just one case, a fast radio burst happened. Unfortunately, we didn't detect it. It is outside the field of view, but it was detected by the Caltech STARE-2 and CHIME telescopes. So this is the this tells us pros and cons of the different types of telescopes. So STARE-2, and basically they're very small telescope, the antenna, but they spread out in many different places. They cover a very wide range in the sky. So whenever something happens within the field of view, they will catch it. But it has to be very bright. So the normal FRBs, they probably won't be able to detect too many. So extremely bright ones they can detect. CHIME-2 is also a wide field of view telescope. They can detect a lot of FRBs actually. Of course, they can detect these bright ones. And FAST, on the other hand, it is a single dish telescope. It is very sensitive. It can detect very faint signals, but for very bright signals, it has a disadvantage because you can only stare at that source in order to see it. So, but the detection by STARE-2 and CHIME was, well, accompanied by a gamma ray burst. So this is what we were expecting. So if the FRBs are indeed associated with the gamma ray burst from magnetars, then we make a direct connection. And this particular gamma ray burst was not detected by SWIFT, was not detected by Fermi. It was detected by HXMT, Integral, and 2 other Conus wind from Russia. And so there are several of them detected. But this is the HXMT plot. Very interestingly, you can see this event had 2 pulses in the radio band. Actually, STARE-2, because sensitivity is poor, only detected the second one. They did not detect the first one. CHIME detected both. And it turns out that this hard X-ray or soft gamma ray burst also had 2 peaks. And if we correct for the delay time the radio wave propagate to us because of the dispersion, then these 2 peaks align with the 2 peaks of the X-ray and gamma ray light curves. So this is actually a very robust conclusion that FRBs are associated with the gamma ray burst of the magnetars. And recall that this particular event, the brightness is 1.5 million Jansky, but normal FRB is 10 millijansky. So basically, this guy is brighter than the other FRBs by 8 orders magnitude, because it is in our galaxy. If we put this particular burst to a cosmological distance, Actually, it is a relatively faint one. The luminosity is actually lower than the others. Okay, and interesting thing for fast is, so during the third epoch, when we observed this source, there were 29 other gamma ray bursts. And we searched very carefully and performed deep observation. And again, they're supposed to arrive in these red lines, and none was detected. So the bottom line is the majority of the gamma ray bursts are not associated with FRBs. So suppose if there were no this detection, we probably will reach the same conclusion as previous people did. Say, okay, the magnetars cannot make FRBs. Then the question becomes, why only 1 out of 30, actually now it's 1 out of 100 gamma ray bursts will make a fast radio burst? There are several possibilities. These are two of them. So the first one is the X-ray burst emission is quite isotropic, which means the emission can be observed from all different angles. The fast radio burst itself, however, could be narrowly beamed, which means only when this beam points towards the Earth we can detect it. In other cases, there might be FRB, but it goes to some other direction. Some other aliens can see it, we cannot see it. So within this scenario, we would expect some cases I call slow radio burst. I had a recent theory paper about this, which means our line of sight could be slightly outside of the beam, and we'll see a longer and fainter burst. So in principle, if we keep observing this source, we probably will detect some of these slow radio bursts rather than fast radio bursts. If this is the case, it will confirm that the emission is highly beamed. Another possibility is that particular FRB or that particular X-ray gamma ray burst is special, more special than the others. This has been seen from these two spikes. The other bursts do not seem to have very sharp spikes here. So this one had two spikes, but there are others also show spikes, so we didn't see radio burst. And another interesting data analysis by these guys, they show that if we care about the cutoff end of the spectrum of this gamma ray burst, X-ray burst, and the other X-ray burst, they found that this one has a higher cutoff energy. So that might be a evidence suggesting that this burst is special. So this is still ongoing problem. So hopefully we'll detect more galactic FRBs, and then we can answer this question better. Related to this is, so now we identify the source of FRBs, at least one source of FRBs, that is magnetars. Then the next question is, how is the radio burst emitted from that magnetar? So what is the radiation mechanism? This is highly technical. I will skip the details. So the bottom line is, because the radio wave is so strong, the so-called brightness temperature is very high. One cannot use the simplest, say, thermal radiation or non-thermal radiation. So whatever we know about radiation, the high energy band, the radiation from all kinds of high energy sources, it's hard to interpret with those mechanisms. Instead, it has to be something special called coherent mechanism. There are two types of coherent radiation mechanism. One is related to the magnetosphere inside the magnetosphere of the neutron star magnetar. The other is far away. So outside the magnetosphere, there could be relativistic shocks. So this one looks like radio pulsar. So it's a pulsar-like mechanism. This look like a gamma ray burst, a GRB-like mechanism. So I will skip the details, but this was the debate in the field regarding the origin of FRBs, even before this discovery. And now we have more and more observational data. To me, it is actually strongly suggesting that emission comes from the magnetosphere, the former model. So these are two observations. This one, I skipped the detail. This is another Nature paper we published last year. So basically, this is a repeating source, and we detected here we present 7, actually 11 total, but 7 of them have this polarization angle measurement. I will skip the detail. The bottom line is you can see the polarization angle. There's a swing. So this one is going up, this one is going down, this one is going up and down. Those kind of features. Those kind of features are very difficult to interpret within this scenario, but it is something like a pulsar. Pulsars do that all the time. So it supports magnetosphere model. This is another paper currently under review in Nature. So this very first repeater, so you probably recall Arecibo detected 11 bursts to begin with. And we actually, a year ago, we detected more than 1,000 bursts. And their waiting time is pretty short. Within milliseconds, they boom, 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 they make a lot of them. Again, this is very difficult to do in this scenario, but it could be done within this scenario. So these observations actually solve another mystery. What is the radiation mechanism of FRBs? Their magnetosphere emission from magnetars. So this is my favorite model done with Wenbin Liu and Paran Kumar, Caltech, and UT Austin. So the bottom line, the basic picture is the magnetar probably did something like inside, internally. There's a crust cracking, and then send some oscillations and send out alpha waves along the magnetic field lines. In the closed field line regions, it will just heat up the plasma and make X-rays. However, if we have alpha waves in open field line regions, which means these B fields will extend to infinity, and these alpha waves will start to, at certain height, it will develop fast radio bursts. And if we get into detail, probably there are bunches with positive and negative charges. I won't get into the details, but this is one of the models. To me, it's quite attractive to understand FRBs. Okay, open questions. There are a lot of them, but 2 of them are, number 1, are there other engines to power FRBs? So we know magnetars can do that, but how about other things? So, and also are there generally non-repeating FRBs? So do we have one-off FRBs? So these are 2 extreme scenarios. This is the most conservative scenario. This scenario is saying that all the FRBs in the universe are made by magnetars. So FRBs, we have active repeaters. Those are very special magnetars formed in some special channels. We don't have those magnetars in our galaxy. And the regular repeaters or non-repeaters, they are the regular magnetars. Those are the ones we see. So within this picture, nothing else, just magnetars. So far, this picture is not contradictory to observations. And another one, actually, I like it better, is that we do have many different categories. This will have a lot more fun. So we have repeating FRBs, we have non-repeating FRBs. For repeating FRBs, besides magnetars, we could have some other things, for example, neutron-star interaction, black holes. And for non-repeating ones, we can have complex star mergers and blitzars and other things. So this is more exciting, but really need a lot more data to show whether any of these will actually exist. Now, back to aliens. So as I said, there were models talking about FRBs produced by aliens, but FRBs are from extragalactic, from cosmological distance. those aliens must be very, very advanced to produce FRBs. And they, then for the recent one, there within 1 month, there were like thousands of bursts. I don't believe any aliens bothered to do that. So, and we know that a lot of the properties of extragalactic cosmological FRBs could be understood within the astrophysical scenarios. But this does not mean that the galactic aliens, the aliens in our Milky Way galaxy, they will not do this. They probably haven't done this. Very likely they haven't done this yet. But if they do, if, say, any civilization very advanced, they wanted to advertise their existence, what kind of signal they will send out? And very likely it's FRB-like. Why is that? Because first, it is short. You don't take a lot of energy, so milliseconds. Second, it is in the radio band. It is not in the gamma ray band. So again, it's very cheap to make. And all the aliens know that other civilizations are studying FRBs all the time because FRBs are in the universe, including us. We are monitoring the sky, trying to detect FRBs. So if they want to send some signal, very likely other civilizations can detect them. So if they really want to broadcast their existence, this is the right way to do it. And I estimated the total energy budget. It's still huge. It's 10 to the 26 ergs, which is about, so E equals mc squared. You need to convert 100 kilogram mass to radiation only and beam it into the radio band. But it's still probably doable for more advanced civilizations than us. Then the question is how likely we can detect this. So this is some fun exercise I did in this recent paper. We all knew this Drake equation. This is the number of civilizations in our galaxy, the star formation. This is the fraction of stars with planets. This is the number of Earth, fraction with life, or the fraction. Well, the fraction means entire lifetime of that planet, including the future, what fraction will make life, and what fraction will make intelligent life, and what fraction will make communicative civilizations. And L is the duration of that civilization. So this one tells us how many, but it is not measurable. It is not very easy to measure. So what I did is, okay, let's really calculate the signal rate. So suppose these aliens are trying to send out some signals and communicate with the other civilizations. They have this n dot, a signal emission, which means per unit time per year, how many FRB-like signal or other signal will be sent out. And this is what fraction can actually be detected by us. And this is the total number of those planets, those civilizations. And finally, we'll get a observed signal rate. By doing so, we actually, given some of the guessed numbers of these parameters, we can make a connection between the observed signal source with the emission signal rate, observed signal rate and with the emission signal rate. So because we are monitoring the Milky Way galaxy all the time to detect the FRB-like events, suppose in the future SKA, after 10 years of operation, only detect the real FRBs, no artificial FRBs, then one can send out one can derive a upper limit of the emission rate of those signals. It is less than 1 per 100 years. I think this is very conservative. I don't think on average aliens will send out the FRB signal every 100 years. So probably we will not get a very tight constraint on this. but this is something you do it for free. So in the far future, if we don't detect, say, after 1,000 years, then we can place a tighter constraint on this. Okay, so far I talked about the observation using other telescopes like the FAST from China, but how about FRB observations from Nevada? This is a possibility. So my friends from Caltech, they're developing something called DSA 2000, which means they will build 2,000 5-meter dishes. They are small each, but there are many of them and spread out in different locations. They operate from 0.7 to 2 gigahertz. Because they are far away apart, they have very spatial resolution of 3.5 arc seconds. So this array will actually make the the true radio camera, which means you can image the sky. Of course, we'll detect a lot of the FRBs. And we are, UNLV is a partner, including Cornell, West Virginia University, Wisconsin. So those dishes will send to all different locations. And right now we are seeking funding from NSF, but I really hope that Nevada, the state, because this will have some site in Nevada, so the state probably can help us to give some support. And yeah, very importantly, private funding is very welcome. Okay, that's all. This is the takeaway message. The FRB mystery is being solved. Many open questions remain, and more excitements yet to come. Thank you.
Thank you so much, Dr. Zhang. This was incredible. There was a couple questions, or were a couple questions in the chat. So are you okay if I go ahead and read those? Perfect. So the first one says, FRBs seem to be generated from multiple astrophysical phenomena. If that is true, how would one differentiate an FRB generated from magnastar precession to one from binary system with coupled magnetic field absorbing rotational momentum?
Yeah, so that's a very good question. So we're talking about multiple possible sources. So again, I was very pessimistic in the past for cosmological FRBs because we are lacking smoking gun signatures. It's very difficult to tell the two scenarios I mentioned and the 50 other scenarios people are talking about. We really need some smoking gun signatures. For example, within this one, I actually show that some guesses. Besides magnetars, we have other things. If they're from black holes and white dwarfs in some other galaxies, very likely we won't be able to tell. However, if they are related to the binaries, for example, the two neutron stars, this is one of my models. If the two neutron stars, we know neutron star will merge and produce gravitational waves. However, let's say 100 years before the two neutron stars merge, those two are already close enough, and the magnetospheres of the two neutron stars will start to interact with each other. And reconnection might happen, particle might be accelerated, and FRBs might be generated. If this scenario is relevant, then there is a way to test it. That is the gravitational waves with a larger separation, say, so won't be detectable by LIGO, but 10 years later, or 15 years later, LISA, which is a spatial gravitational wave detector, it will detect lower frequency gravitational waves, and those actually could test this. So my prediction is, okay, when LISA is in sky, just stare at some of the repeating FRB sources. If they are from this scenario, then those sources should emit long wavelengths gravitational waves. These are less likely to be identified unless they happen in our galaxy. So just like the magnetar, before this one, we never knew that magnetars can make FRBs. However, if we have something like STAIR2, something like DS2000, we can monitor the entire Milky Way all the time. As I said, the FRB rate is very high. So if we are lucky enough, probably we will, very likely we'll detect more FRBs in our galaxy, but probably most of them are from magnetars. But if another FRB, galactic FRB, comes from the, say, galactic center, or from a X-ray binary source, we know there's a black hole there, then we can prove that black holes can make FRBs.
Awesome, thank you. It looks like there's just one other question, and it is from Michael Spencer, and the question is, are there any future telescopes, equipment, or projects planned that will detect more FRBs and maybe discover more details about their sources?
Yes, so SKA is the major thing. It's international collaboration, so it will have many telescopes in a much wider spread out in different continents. So they will detect a lot of things, a lot of FRBs and other sources. So that will probably happen in 1 to 2 decades.
Awesome. And another question says from CL Huang, you mentioned the absolute brightness of the galactic FRB source is dimmer than extragalactic sources. Besides this, is the galactic FRB behaving very similar to other events?
Yeah, that's a very good question. Yes, it is 20 times dimmer. Other than that, I think it is wider. So let's just look at the, yeah, so you can see the duration is several milliseconds. So this is 20 milliseconds. You can see they're wider, luminosity is lower, but this is consistent with the picture showed earlier. So the repeaters are typically wider and one-off ones are narrower. And one-off ones are typically far away and probably the luminosity is higher, that they are brighter. And repeaters, because we stared at them and using very sensitive instruments, and a lot of detected bursts are fainter and they're wider. So there might be a anti-correlation, which means when you get into lower luminosities, it become wider. Theoretically, if everything is, as I just showed, slow radio bursts. Yeah, so theoretically, if we have different viewing angles, if the FRBs are beamed, if you look down into it, you will get a narrower burst. If you see it slightly outside that cone, you will see a wider burst.
Excellent. So this will be the last question, and it's from Bernard, and he's asked, is there a signature of FRBs in the 21 cm line of H along the line of sight?
Oh, that's an excellent question. It turns out that the FRB frequency is coincident with the 21 centimeter line. There is no such kind of signals yet, but people have been considering all kinds of possibilities, and they're trying to do a search. And people also discuss the possible, not really, there's a line emission from the FRB, but it could be some related environment. For example, in the FRB emission region, there's neutral hydrogen. In that way, you can see the both. So hopefully, more sensitive telescopes can do that. FAST, well, in principle, has the sensitivity, but so far, well, it has the sensitivity to do short duration burst searches for continuum observation, we actually require even larger aperture. So in that case, VLA and those telescope arrays probably is better to do that. That's a very excellent question.
Well, great. Thank you so much again, Dr. Zhang, for your time and for joining us today. And thank you to all of you for attending. I know we just go a little bit over the 1 o'clock hour, but I'm so glad you stuck with us because those questions were great and it was great to get those answers. So thank you again. And again, we will be placing this on the College of Sciences website, as well as the College of Sciences YouTube page. So if there's something you missed or maybe didn't quite catch something, you can always go back and watch the presentation. So thank you again for coming today and have a great afternoon.
Thank you, Corey, and thank you, everyone.